In this video, we're going to take a look at Euler's method. And what Euler's method allows us to do is to approximate function values. And it's especially useful when we have a differential equation that we cannot solve using our separation of variables. If we could solve it, we could find the actual function and just plug in the value and find the actual function value. But when we can't solve it, Euler's method gives us a way to approximate that function value. Now I'm going to start with a very simple differential equation. dy dx is equal to x. This is actually solvable for us, but we're going to use this to kind of explore Euler's method and understand better what it does for us. We're going to let y equal f of x such that f of 1 is 1.5, and we want to approximate the value of that function at 1.4 using Euler's method with two steps. And so let me show you what that means. If my differential equation dy dx is just equal to x, then we know that the solution curve is going to be a parabola because the derivative is x. So I'm going to draw a curve here and mark this off. Say this point here is at 1. And then I'm going to label that point to be at our 1.4. So kind of zoomed in pretty good on this curve here. Now we have, technically we've used Euler's method before, but with only one step. Whenever we do a tangent line approximation, that's basically, we're doing Euler's method, but we're just using one step. And let me show you what that means. I could find the equation of the tangent line here at the point 1, 1.5. And that tangent line would look something like this. And then we could plug in 1.4, and that would give me this value right here, which we can see is, kind of close to the value that we're interested in, but not especially close. But let's go ahead and find that value. Tangent line approximation. If we do our tangent line, y is equal to f of a, which is 1.5, plus f prime of a, that's going to be my slope. Dy dx is just equal to x, and my x coordinate, my at point here is 1. So my slope is just going to be 1 times x minus my at point, which is 1. And if I want to approximate 1.4, I'm going to plug that in for x. And if I calculate that all out, it's going to give me 1.9. So this point has the coordinates 1.4, 1.9. And that would be an okay approximation of our function value up here. What Euler's method does, though, is says, okay, let's take this same strategy and break it down. What if we did this process twice? Could we get closer? So instead of going all the way from 1 to 1.4, we're going to break up the trip right here at 1.2. And I'm going to use this same tangent line equation, but I'm going to plug in 1.2, and I'm going to find the value of that point. And then what I'm going to do is use this point and the slope of the curve up here at this point, and I'm going to write a new linear equation. I'm not going to call it a tangent line because it's not actually going to be touching the curve. It's going to go through this point that we find ourselves, but we're going to use the slope of the curve. And so that slope is going to send that line maybe like this. And if I plug in 1.4 to that line, that's going to give me the coordinates of this point, which you can see is much closer to the actual value that I'm interested in. So how do we get to this point? Well, I'm going to set up a table here. And we're going to start with a f of a, which is going to be the point that we're given, this point here, 1, 1.5. And I'm going to do my tangent line approximation and I'm going to end up with a new point called B f of B. But then that point is going to become my new A f of A, and we're going to do the tangent line again and find our final point. When I find my new B f of B, which is this point right here, my x coordinate is going to be 1.2. And so this new x coordinate is going to be 1.2 with whatever value we find here. And then I'm going to go the new step, and we'll end up at 1.4. So this change here from 1 to 1.2, and then from 1.2 to 1.4, that's called a step size. When we're asked to use 2 steps, we have to figure out how wide those steps are going to be. What's my change in x going to be? And for this example, we're wanting to approximate the value at 1.4. We're starting at 1, and we're going to take 2 steps. So that gives me a step size of 0.2. So I start at 1, I go to 1.2, and then from 1.2, I go to 1.4. Here in the middle, we're going to use our tangent line formula. So the f of b is going to be approximately equal to whatever my f of a is plus f prime of a times, and I know we're used to x minus a, but this is going to be our step size, our delta x, which in this case is going to be 0.2. In fact, I'm going to just go ahead and write that in. My step size is always going to be 0.2. So if I plug in 1.5, that's my f of a, plus I need f prime of a, and I'll just write this down here. Remember that f prime of x is going to be equal to our dy dx, our differential equation, which is just x. So f prime of 1.5, I'm sorry, not 1.5, f prime of 1, 1 is our a value. That's going to be equal to 1. So my slope here is 1. And 1.5 plus 0.2, that would give me the point 1.2, 1.7. And so these are the coordinates of this point right here, 1.2, 1.7. That's this point. So now we're going to use that point and find the equation of this green line. So my new f of a is 1.7. My new slope, f prime of a, which is 1.2, so that's just going to be 1.2, times the 0.2, which is still our step size. And if we calculate all that out, we're going to get 1.94. And so the coordinates of this point, 1.4, 1.94. And so using Euler's method, we're saying that f of 1.4 is approximately 1.94. All right, let's look at another example. This time we have the differential equation 2x minus y, and this is one that we can't solve. These are not separable, and so if we want a value for the function at 2, then Euler's method is our option here to find an approximation for that value. So we're going to let y equal f of x such that f of 1 is 3. We want to approximate f of 2 using Euler's method with 2 steps. So first thing I'm going to do is find that step size. Our delta x is going to be equal to the ending x value, which is 2, minus the beginning x value, which is 1, divided by the 2 steps that we want to take. And I get 1/2. And so now I'm going to set up the table. We're going to start with our a f of a, end up with b f of b, and in between, f of b is going to be f of a plus f prime of a times our delta x, which in this case is 1/2. In fact, I'm just going to go ahead and put in 1/2. That's our delta x. I'm starting at the point 1, 3. If my step size is 1/2, If I start at 1 and I go over 1/2, then I'm going to end up at 3/2, which will be my new x over here. And if I go another 1/2, that's going to get me to 2, which is where we want to end up. So now I'm going to do my tangent line formula here. F of a is 3 plus f prime of a, or dy dx at this point. So let's calculate. I'm going to calculate this down here. Dy dx at the point 1, 3 is going to be equal to, remember my dy dx is 2x minus y. So 2 times 2 minus 3. And that is, oh, not 2 times 2 minus 3. Whoops, sorry. Let's try that again. 2 times 1 minus 3. I was already multiplying it out in my head. So that equals -1. Sorry about that. So we have 3 plus a slope of -1 times 1/2. And that's going to give me 5/2. So now my new a f of a is 3/2, 5/2. And so now we're going to go through the linear equation again. F of a is 5/2 plus, I need to calculate a new slope, dy dx at 3/2, 5/2 is going to be 2 times 3/2 minus 5/2, which is 6/2 minus 5/2, which would give me 1/2. And so to calculate my new f of b, I have 5/2 plus 1/4, which would be 10/4 plus 1/4 if I change that to fourths to get a common denominator. And that's going to give me 11/4. And so with Euler's method, we're saying that f of 2 is approximately 11/4. Here's our final example. Dy dx is equal to y over 2x. Y is equal to f of x such that f of 4 is equal to 8. And we want to use Euler's method to approximate f of 0 with 2 steps. Now, what's really important to notice in this question is that I'm starting at a value of, starting at an x value of 4, and I'm ending at 0, which means in this case, we're going backwards. So when we calculate the delta x, we're always going to do the ending point minus the starting point divided by the number of steps. So -4 divided by 2 is -2. This time my step size is negative because we're going backwards. I'm going to set up the table. A f of a, b f of b, and my f of b is approximately f of a plus f prime of a times our delta x, which in this case is -2. Just going to go ahead and put that in for my 2 steps. I'm starting at the point 4, 8. If I start at 4 and I go back 2, I'm going to end up at 2. And then if I'm at 2 and I go back 2 more, then I end up at 0, which is where we want to end up. All right, so my f of a for my first step, f of a is 8. And then I need a derivative. Dy dx at the point 4, 8 is equal to, my dy dx is y over 2x. So 8 over 2 times 4, which would give me 1. So my slope is 1. And 8 minus 2 is 6. So my new point is 2, 6. And f of a is 6. Plus, I need to calculate a slope, dy dx. At the point 2, 6 is going to be y, which is 6, over 2x, or 2 times 2. And so that is 6/4, or reduces to 3/2. And I have 6 minus, what is this? 6, negative 6 divided by 2. So just 6 minus 3 gives me 3. And so using Euler's method, f of 0 is approximately 3.